So we're going to look at 3 ways to use trigonometric substitution. There are 3 techniques, and it's all based on what we see with the square root. So if we have an integral with a square root of a squared minus x squared, where a is some constant larger than 0, if we use a substitution for x is equal to a sine of theta, then we know if we take the derivative of this, it becomes the a stays the constant, sine becomes cos d theta. And if we use both of these facts, well, primarily the first fact, and we say a squared minus x squared, we can replace your x squared with a sine theta and square it. So a squared sine squared theta. Then we can factor out an a squared out of it. And you're left with 1 minus sine squared theta. And we know that since sine squared theta plus cos squared theta equals 1, we can rearrange that to isolate so that 1 minus your sine squared theta is going to equal cos squared theta. So we can replace that here. Then we can say the square root of this entire thing. So we square root this entire thing right here, and we're going to get a cos theta. So now if we look at an example that's going to use the substitution method, we can then say that our x, because we have here in this format a squared minus x squared, a squared minus x squared, our a in this case is equal to 3, and it falls into this format, so you can set your x, just like we have up here, to be a sine theta. So a is going to be 3 sine theta. Dx, we just take the derivative of that, it's going to be 3 cos theta d theta. And then we can say that the square root of a squared, so 3 squared, minus x squared is the same thing as a, in this case 3 cos theta. So we can use this for our substitution when we're working here. So how we're going to use the substitution, we're going to take this portion here, so 9 minus x squared all square rooted, so this portion right here, and we're going to replace it with 3 cos theta. So now we've got the integral with 3 cos theta on the denominator. My x squared, I'm going to use my x definition of 3 sine, and I'm going to write that as 3 squared sine squared theta. So basically squaring my x term. My dx is equal to 3 cos theta d theta. So I'm just going to write it as 3 cos on the side here, d theta. Then you can see some things are going to start to cancel out. 3 and the 3, the cos and the cos, and then I'm left with the integral of 9 sine squared theta d theta, which then you can move the 9 out front and have my sine squared theta d theta. Now we know from last day with our tables that we worked on, we can now write this as 9, and the whole thing is going to be in brackets. So now we have sine squared x dx in the table. It tells you, in this case we're using thetas, theta over 2 minus 1/2 sine theta cos theta plus c. Now that's all in terms of theta. What we now need to do is replace my thetas with the information we have here. Using the substitution, I can use this to figure out that x over 3 is equal to sine of theta. To isolate for theta, we use sine inverse. So sine inverse x over 3 is equal to theta. So to substitute it back in, we can automatically say 9, and then we'll say 1/2. Theta in this case is going to be sine inverse of x over 3 minus 1/2. Now, if we were to write sine of theta, and theta is the sine inverse, it's just going to become x over 3. So it's a half times x over 3. What's a little bit different though is cos of theta. We have our identity here in the red box. So I can actually write cos of theta as the square root of 9 minus x squared all over 3 plus our constant. And the constant's times by 9, but it's still a constant regardless, so I'm just moving the constant out front. Now to simplify this down a little bit, you get 9 over 2 sine inverse x over 3 minus, and in this case here, that's 3 times 3 is 9 on the bottom, so that cancels out with the 9 on the outside, so you're left with just a half times by this, x square root of 9 minus x squared plus c. So the next format we're going to look at is when we have an x squared plus a constant squared, so an a squared. Again, where a is greater than 0. Now the last one we looked at was our constant squared minus our x squared. This one now is the addition of the two. So the order really doesn't matter, but they put the x squared first. In this case here, we're going to again choose a way to identify x for a substitution. It's going to be a tan of theta. And then we take the derivative. So the derivative of tan theta is secant squared theta, and the a is a constant, it stays there. So it's a secant squared theta d theta. And again, we substitute in our x substitution into our x squared plus a squared. As you can see here, we square both the a and the tan. We factor out an a squared again, and then our tan squared plus 1 is just the identity of secant squared theta. So if we take the square root of this whole thing, we get a secant theta. So for this example here, we're going to have our a value is 4, because 4 squared is 16. And we're going to set our x is going to equal our 4, or a tan theta. Our dx, we take the derivative of that, this is going to be 4 secant squared d theta. And then our square root of x squared plus a squared, so 16, is going to equal 4 secant theta. So again, we're going to substitute in what we know. The integral of 1 over, and my x now becomes 4 tan theta. My square root of x squared plus 16 becomes 4 secant theta. And my dx becomes 4 secant squared theta d theta. And again, you can see that things cross out. One of the secants will cross out with a power. So then I have the integral of, in this case here, secant theta all over 4 tan theta d theta. You bring the 1/4 out, and we know that secant is 1 over cos, and tan is sine over cos. So if I'm dividing these two, you multiply by the reciprocal, and then you get 1 over sine. So we get that. Hopefully everybody's okay with multiplying by the reciprocal and crossing out your coses. Now we know that 1 over sine is the same thing as cosecant theta d theta. And if you look in your table from last day, there's actually a simplified form. So you have ln of cosecant theta minus cotangent theta plus c. And again, you have to substitute back in. That's the important part of this. So to do that, again, you'll want to look at how to simplify a few things. So if we look at x is equal to 4 tan, and if we isolate x over 4 equals to tan, with that same logic, if we do 1 over tan, 4 over x is going to equal cotangent. So we can replace that portion. So if we consider this here, to find the actual angle, we can use tan inverse of x over 4 is going to equal your theta. Then you can plug theta into your cosecant to figure out what the cosecant value is. If it helps you to look at a triangle, tangent just means opposite over adjacent. Opposite is going to be x, adjacent is going to be 4. That means when I square these and then square root it, I get this side here. Now cosecant is the same as 1 over sine, so sine is x over square root of x squared plus 4, so 1 over that becomes then just the square root of this all over x. So we get 1 over 4, the ln of the square root of x squared plus 16 all over x minus 4 over x plus your constant. The last format of the integrals that we'll look at that have square roots is when we have x squared minus a squared. Again, a is a constant that's greater than 0. And we use the substitution where x is equal to a, the constant, times secant of theta. The derivative of this is then becomes a secant theta tan theta d theta. And then by the same logic as we've talked about before, the square root of x squared minus a squared is a tan theta.